Okay, so the plan for today is we're gonna continue the particular derivation that I started last time. And so again, last time I was hoping that I can go a little bit more, so it can be sort of helpful for your homework for submission, but hopefully it's still, not too late. And again, it's different models. Back then for the homework, which I will post the solutions later, but that is, in some way you can consider that as a hierarchical model, and then you start to have different layers of the prior. So it's still the same gist. So in general, what we're hoping to do when you're doing full posterior conditional distribution derivation is you get the joint of all of the joint posterior of all of the parameters, and then you do it one by one. Okay, so in different settings, you might have different tricks, but overall, the same procedure follows. So let's just come back to the hierarchical model that we covered in class last time. That's where we give a normal likelihood model for a normal sampling data model for the observations, and then we're doing the okay, yeah. So so let me actually just rewrite part of it. And I will give you some time to work on the derivation, then we look at it together as a class. Okay, so again, the case that we are working with is that you have data model, which is group specific, right? So we are working with this case that for each group J, you have the observations Yij follows a normal distribution with the group mean, and you share all of the standard deviation across all of the groups. So the index, again, very important to keep track. So there are Nj observations in each group J, and then their total capital number J, capital J number of groups. So that's the data model, and we know that the prior we have for the mu, it's a two-stage prior. So we have mu and tau as the mean and standard deviation for all of the mu j's, and then we put hyperprior for mu as normal mu 0 and gamma 0, and then also for tau we work with the precision, right? So gamma, I think it's alpha tau, and then beta tau, 1 over tau squared, sorry. And then lastly is this 1 over sigma squared. So that's not a hierarchical prior, right? It's just one prior that we, one parameter in this case. So we have gamma, and then alpha, sigma, and then beta. Beta sigma, okay? So last time I was trying to make sure that we all know how the hierarchical model is set up in terms of when you're trying to write the joint posterior. So let me just start that for you. So what do we have? We have all of the parameters, which includes, let's see, capital J number of mu j's, right? And then mu, tau, and sigma. Yeah, so you need to include all of them because they are all the parameters. Some of them are hyperparameters, but because we put hyperprior for those hyperparameters, so you're still gonna go to derive the full conditional. So what you have here is, so I'm writing mu j prime, just all of them, represent all of them. And then mu, sorry, and tau, and then sigma, right? And we have all of the data. I'm using curly bracket to represent it's a large group of them and nested in terms of different groups. And what else do we have? We have, so in the end, I think we give numbers for those parameters or hyperparameters, right? Yeah, but they're being conditioned. So I think just to be consistent and not easy to make error later, I would rather just keep everything. I mean, you will see that all of those 6 of them gonna always stay after the conditional sign. And but it's still a good practice to keep track of them, so you know that they will be given fixed numbers. Because if you imagine that you're going to try to write the give sampler by yourself, like writing all of the loops and stuff, you're going to put placeholder for them anyway. So I think it's a good practice to keep them there. All right, so what is this? We know that the joint posterior, this is true for all of the stuff that we work with. So the joint posterior should be proportional to the joint prior. So now you see that I start to write, because all of those mu0, gamma 0, and then the alpha and betas, they are the values that we use in the priors and the hyperpriors, right? So essentially, what is conditioning now, like those should go into the after the conditional sign in your joint prior. And so keep track of what they are. So this is what I mean, that I'm trying to write the prior in terms of a conditional, but this is, I mean, it's still a prior, a joint prior, and I'm only just conditioning the fixed numbers that I'm going to give later. Okay, so this is joint prior. Okay. And the likelihood is, so I'm going to use just to write L. And then it's whatever that's related to the parameter. So sometimes people might want to just conditioning on everything else, but just for simplicity, that's what the joint likelihood should be. Okay. All right, so the goal is finally derive each of the full conditional distribution, but to start, we know that we should first of all I think it's okay. Yeah. So first of all, we have to make sure that we know how to express this joint prior, right? So it's given to you through 4 lines, and the first 3 are about the mu j's, and it's a 2-stage prior there, right? And the last one is about just 1 stage, or like single prior for sigma. So let's work on together how to get this joint prior, and I'll let you to try to do the rest first, okay? So let's see. So I will erase whatever is here, and I will try to just get the joint prior for you all. All right, so the joint prior, let's do this one by one. So we want mu j, mu tau, sigma, given whatever that is. I'm just going to use this as a simple notation. So what do we have? We first of all have all of the mu j's coming from the same normal, right? So what that means is, and they're IID. So that tells us that we should have the product of all of the marginal density, univariate density, which is a normal for each of them. So let's start writing the density here. So it's 2 pi, and it's tau squared, because that's what the standard deviation is. And then it's in the exponent negative 2 tau squared, and then mu j minus mu squared, right? And just to be clear, it's the product of the whole bracket. Okay. All right, so that's the part about mu j. And what about mu? Mu is a normal, and mu is single, right? So you do 1 over 2 pi, so it's gamma 0 squared. And then in the exponent negative 2 gamma 0 squared, and then mu minus mu 0 square, and then the whole thing. Sorry about that writing. It's the same. It's a pair, the parenthesis. Okay. All right, so what's the gamma for 1 over tau squared? So you notice that we're working with the precision. So whenever you write it, you can just write 1 over tau squared as the random variable, and then you put all of the terms for them. So that I do have to look at my notes because I don't remember. Okay, so it's beta tau to the power of alpha tau divided by gamma alpha tau. So I'm working on 1 over tau squared here. And we have the random variable, which is 1 over tau squared, raised to the power of alpha tau minus 1, right? And then the exponent is negative tau, beta tau, and then the random variable, which is tau squared. Okay, right? And lastly, I have the part about, so it's beta sigma, alpha sigma, divided by gamma alpha sigma 1 over sigma squared to the power of alpha sigma minus 1, and then the exponent negative beta sigma 1 over sigma squared. That's what I have. Right? So you see that like I just go it like you go one by one, and I think we can even add some in-between steps just to make sure like the math is working. But when you get like familiar enough about this, you can just go ahead and then get in the density directly. Okay. So the only thing I would make sure that you don't make mistake about is about this term, because everything else is univariate in some. I mean, this is univariate, but we're doing the joint. So what you have is essentially. This is proportional to, so all the pi's they can go, and you need to make sure that, first of all, you work with 1 over tau squared, just because that's the random variable that we work with, okay? It is about tau, but it's 1 over tau really, 1 over tau squared really that we're working with. So keep consistent, so that means this whole thing is what? Is 1 over tau squared 1/2, right? Because you take the square root of that. And you're what? You're doing j copies of them. So this becomes capital J over 2. Okay. And then in the exponent, whatever is the product outside becomes sum, right? So you have j, and then mu j minus mu squared. So this will be, I think, an important simplification before you move on, just because it involves the product term, and you want to make sure that you keep track the terms correctly. Okay? And then, of course, you can start to recognize, I mean, those 2 pi, you can throw them away later as well. All of those goes away. Here as well, right? Yeah, because essentially, what are those like beta sigma and alpha sigma, all of them, they are in here. They're being conditioned, okay? So that's why they can go into the proportional sign if you just try to write the joint prior. Okay? All right, so have whatever terms that you think is important to keep down, like on your notes, and then I would say now let's just work on how to write the joint likelihood really quick. So for the likelihood, again, I think I did it briefly last time, but let me just show you again. So now you have observations in groups, and there's still n number of observations, but they're broken into j different groups. So you have different counts. You do have different number of observations in different groups. So you just have to do it like carefully. So first of all, I know that, so I'm trying to, and so first of all, it's Yij. So it's being conditional, right? And I know this is a normal density, right? So this is for each observation. That's what it follows, right? And a good thing to keep track with, I think, is to write out the products first correctly with this. So what do we have? So first of all, we know that within the same group, which is J, we have I from 1 to Ni, right? So that's all of the observations within one group. So I product all of them. I put a bracket. So this is representing the joint density of all observations in one group J. Right? So essentially what this is, if you try to write it, is Y1J, Y2J, until YNJJ. That's the joint. Okay? So this is only one group. And we have capital J number of groups. So what you do is you're just going to put one more product out of this. So you're getting all of the J's. Okay? Yeah. And then, of course, this F is the normal density. So you express whatever that is. Okay? So I'm going to pause here. I will ask you to work out the joint likelihood. You need it just because later you have to collect terms about mu J, about sigma. Yeah, I think those are the main things that you need because mu J and sigma, they both go into the likelihood. And then later you will need them when you're trying to derive the full conditional. Okay? So I'll pause here. I will write something on the board and then later you can compare it to. Okay, I think I maybe went too fast. So let me just talk about this again. And I think I will have to erase some stuff so I don't, yeah, so I will erase whatever is down here. Hopefully you made a note. If not, hopefully you remember. And we're gonna come back to this later for sure. But let's first of all get a good understanding of how the data model is. So now we know that all of them are, oh, I should just clear. So what do I have? We have that's the normal data model, okay? So, and then I is from 1 to NJ, and then J is from 1 to capital J. Okay, so again, this is how many groups there are, and this is how many observations in each group. Okay, so when I write this, I wrote for every observation, okay? And I was saying, so, okay, what is joint likelihood? Joint likelihood is I'm trying to find, so I use F generically, that's the density, the joint density. If I try to express all of the YJs together, given whatever that is given, needed in the parameters, I should say. So if I try to expand it, what do I have? I mean, if it's doing it tediously, or it's going to be like Y1, 1, right? Y1, let's say Y2, 1. So let's do one group at a time. So for the group 1, I have N1 of them, right? So this is what? This is all of the observations from group 1, right? And I do that for what? For group 2. So it's Y1, 2, Y2, 2, and then Y2, and 2, 2. So these are all observations from group 2. Okay, so I'm not introducing any of the normal density for now. I just try to make sure that I understand what does it mean to have all of these observations get a joint density for all of them. Okay, and in order to include the last group as well, I'm going to have Y1 capital J, Y2 capital J, YNJ capital J. Okay, so these are my group J. This is okay, right? I'm just trying to list all of the observations that I need. Okay, so the product that I showed you earlier really, I think, comes from here. So first of all, let's see. So I could do, so first of all, we know that like across the groups, I mean, the sigma are being shared, but observations are still IID, right? So one thing I can do is I can start to write the group separately, and I'm just making the product of them, sorry, because they are independently distributed. Right? So I can do this until my y1j, y2j, until ynjj. Okay? So from the joint, I start to see that I can factorize them because they're independent. Okay? All right. Okay, so now let's just work on a generic, okay, let me just write a generic one here. So it's going to be 1 small j, 2 small j, until 1 nj small j. Okay, so this is a generic one that I will work on. So how can I further expand this one? So this is what, so this is the time that you should go back to the normal density that the data model at the first line that I show on the top, okay? Because that is to say, fix a j, I know that all of the observations independently follow a normal distribution, okay? So what this says, this is, I know I will have my y1j, because they're independent, so I can multiply them, 2j, and then ynjj, right? Okay. So that's where the first product comes into play. Because if I just generically write yij, given mu j and sigma, so again, I put the given here just because I know those are the parameters I'll be working with. Okay, later it's not necessary, but you would know that's what you're gonna need. And the product goes from 1 to nj, because I have nj observations of them. Okay? Okay? Right. So pretty much in green, I express the joint of observations in one group by a product of the univariate univariate density yij. But I fix the j in this case. Okay? All right. So then we also know that in order to get all of the other groups, I do this for the same, for each group separately. But in the end, as you can see that we're taking the product across the groups, right? So that means, let me use a different color maybe. So that means in order to get this right, I already have the genetic expression for one group, which is for a group J. So it's the observation goes from 1 to nj. And then I have my yij given mu j sigma. This is for one group, okay? And I need for capital J number of groups, and they're all independent. So what I do, I just take another product outside. Okay? So that's J from 1 to capital J. And that was, I think that was what I wrote at the beginning, earlier in green on the upper right. And yeah, so this is how you break it down. Okay? But again, once you get like familiar with this, you don't even have to do this step by step. You know it's going to be product. Mm-hmm. Make sense? All right, so how can I write this joint? So maybe let me just like change it here. So I'm going to keep my product here, and I'm just going to introduce this normal density in here. What is the normal density? Is mean is mu j and standard deviation is sigma, right? So what is that? That is 1 over 2 pi sigma squared for each observation. that is exp negative 2 sigma squared yij, because that's the data, random variable. And this is mu j. This is the square. So I close this, I close this, and I close this. Okay, let me just. Yeah, so make sure that you understand the final term in purple. And now I encourage you to try to expand it, because you don't want those product outside. You will want things in sum in the exponential term. Okay, so do it step by step. I would say do the inner product first, and then the outer product. Okay. Yeah, just try to play with it. In fact, later when we try to derive the full conditional posterior distribution, let's see, might not, yeah, it might not be necessary that we have like the full expression for all of the products being expanded, but at least it will be a good practice. At least, okay, so now expand the inner one, okay? So keep the product outside about j from 1 to capital J, but expand the inner one to make sure that you know how to write the joint of all of the observations in the same group. Question, you have a question? Yeah.
Yeah. Since some of the constants are like nested within 2 layers of like product, so like it just generically when doing these kind of problems, when we're deriving it, we just like get rid of it on like the first step. I'm not sure. Like,
you mean which ones? The
like the 1/2 pi sigma squared.
Oh yeah, those ones. You're right. Yeah, like 1/2 pi, like square root of 2 pi, they can always just go away early on. Yeah. But anything about the sigma, you have to keep them there. And mu j is of course, and yj is just the data. Okay, so it looks like most of you get it. So let me just get this across, and then we can finally go to the full conditional. And so for now, okay, I will erase all of this, and I'll just work on the purple piece. Right, so the expansion for doing this joint, the inner joint, I mean the inner product here is what we focus on, say only this part, right? Okay, so I do this. So I will still keep the J outside, right? And yeah, since now I'm just working term by term, I wouldn't throw away any constants for now, but typically you can just like do proportional sign and then get them away. All right, so what's in here? So we know that the product, this product sign governs whatever goes in here, right? So you have to make sure that you term by term, make sure that you have the product right. So it's 1/, so the thing is this part again, typically I wouldn't keep track of them, but for now, let's just do this. And this should raise to the power of nj, right? Because there are nj of them, okay? And for sigma, again, earlier I was saying because sigma is a standard deviation, but we put like prior everything on 1 sigma squared. So I recommend you just to work with 1 sigma squared. So that is, you have 1 sigma squared. And earlier, because this is what? Down here, we take the square root of that. So it's going to be 1/2, right? But because we have nj copies of them, so it's nj. And lastly, in here, denominator stays the same. The numerator, just the sum of all of them, okay? Which means you don't even need to do much work, I would say. So it's make sure it's I from 1 to nj, and then yij minus mu j squared. Okay. Yeah, so I should mention, it's probably sufficient, I think so, it's sufficient only expand the inner one, because the later one, as you can see, soonish, if you start to derive the full conditional, let me use a different color. If you start to derive the full conditional, so say, because each mu j is different. Okay, we focus on one mu j at a time. And generically, you can work with one mu j. So let's say just one mu j. And I'm going to use this notation. You can use this as well, just to mean that I'm conditioning on everything else, whatever, like the data, the other parameters, the hyperparameters. So we know that this, we're only going to collect terms when we are working with mu j. We're only going to collect terms about mu j, right? So that's why I'm saying that for the joint density, for the likelihood, yeah, don't even expand this, because it's just going to get more complicated. We don't even need that, because when we work with a particular j, the data from other yij, they don't matter. Okay? So work with the inner j, and then let's say, sorry, the inner product, and then this is what we have. So obviously, for the full conditional for mu j, we don't need those, it's fine, right? This is constant as well, right? What matters is in the exponent, so you have to keep that. And what else do you need? You need the prior about mu j, right? So essentially, I'm going to write this for you, and then I'm going to pause and let you work on it. So now I'm using the proportional sign. So I'm going to have I from 1 to nj, yij minus mu j over 2. Square root squared. And then what was the prior? Anybody remember for the mu j? It was the normal mu tau, right? So that was, so again, the 1 over square root of 2 pi tau squared, they don't matter anymore. And also, yeah, that part doesn't matter. So you're only going to have another exponent related to mu j, and that's in the prior. So that's what, 2 tau squared, and then mu j minus mu squared. So this is the only two terms that you need, I think. Let me just double check. I don't make a mistake. Okay. Yeah, these are the only two terms that you need when you try to derive the full conditional for mu j. Okay? And now try to do it. It's going to be a normal. You will see it. But you have to expand the squares a little bit and then complete the square. So this is the trick that we saw before when we introduced the normal model. But now, of course, everything gets more complicated because you're having a hierarchical structure here. But the gist is the same. Okay, so I'm going to pause here a little bit and let you work on that. So just a quick comment. Some of you are thinking about, okay, I have, say, like once I expand the square term, I will have like mu j squared, and then some other stuff, like can I cancel things? The issue here is you're dividing with different sigma square, variance, right? Yeah, so you actually have to keep all of them together. So I would just suggest you expand the first term, and then you can throw away terms about yij only because they're the data. Okay, you have to keep them. You have to keep the terms about mu j. So obviously, you're going to have terms about mu j squared and mu j, right? And you have both types in each of these exponential components. Okay, so keep them. And then at the end of the day, you can start to realize, we did this before when we were covering the normal model, that you're just going to collect all of the terms about mu j squared and all of the terms about the mu j, and you have to complete the square. In the end, that's going to give you a normal density. Okay, so that's my hint for now, so take your time. I will start doing it on the board, and you can check your answers. So I'm only working on that, mu j. So I have, what was it?
Never.
So this is the Yeah, the two parts from the data, I mean the likelihood and then the prior, okay? So first of all, you can expand the square, and you have to make sure that you keep the denominator there because they are different. You cannot cancel anything at the moment. So what you have here is you have, let's see, I'm just gonna do, like I'm gonna skip some steps, but just quickly get to the final point is you're gonna have nj copies of mu j squared, okay, right? And then the cross term, it's gonna be summing over the i's, right? So I'm gonna have -2 mu j, and then summing over all of the i's about yij. Okay? So the reason why I can put mu j before the summation is because the summation happens for I. Okay? Mu j is given. So again, I think doing this exercise can also give you a better idea of how the model is doing. Okay? You're essentially modeling them separately, but there is this common sigma down here that you have to keep track about. Okay? All right, and then for the second term, it's 2 tau squared. And then, so you notice that in the first term, I already throw away those yij's. Okay, I don't care about them. And here will be mu j squared minus 2 mu j mu. And then the squared mu can go as well. Right? Mm-hmm. Okay, so next, because I know, I mean, this is product of the two exponential term, I can just work as the sum of the inner parts, but I want to make sure that I collect terms about mu j squared as one, and collect terms about mu j as another, because then that's where you start to see that you can complete the square and then get your normal density out. Okay? So what I can do is I will have, so what I'm doing, okay. I'm not throwing away any terms now, so I'm going to give an equation, equal sign, I mean. So essentially, what I have is, okay, I put out the 1/2 outside because, you know, later when you try to recognize it as a normal, there's always this 1/2 as a constant, -1/2 in there. So you can put that out first. And what I have in front of mu j squared is this nj over 2, so 2 is out, so it's nj over sigma squared, right? That's the contribution for the first term, plus 1 over tau squared. There's a 1 here, and then that was the tau squared here. So this is whatever that I will have about mu j squared. Okay? And then also now I can work with my mu j term. So essentially, so remember we put out the 2 from the denominator, but the numerator still has that 2. So don't forget, don't throw it away. So what you have is it's still going to be negative, and you're going to have, I think, 2 times the sum of yij, and its I goes from 1 to nj. Divided. It's your computer, right? Divided by sigma squared, and then plus, because I put a parenthesis, plus I guess 2 mu over tau squared, and this is the constant that I have in front of mu j. And I think now I'm done. So this is minus, so I have this bracket and then a closing parenthesis. Okay. Yeah. So at this step, I hope you feel like start to refresh your memory. We just did this before when we're working with a normal model, right? You have square terms, whatever in front of it, and you also have the like just itself, mu j. Okay. So what we know is this going to be related to the precision, okay? And this going to be related to the mean. Okay. So once you get to this step, you can actually just read it off. So finally, we have the full conditional posterior distribution of mu j going to be a normal. This I won't go through again. Convince yourself whatever way you can think of, but do this. So it's the sum of all of the yij. I would say divided by sigma squared. So that's, this is the, let me say mu over tau squared. So that's whatever the term coming from the second constant here. And my precision is the first term. And then my precision, because this is precision, we use, let's see, yeah, I think to be 100% correct, you have to do this because we're using square root, I mean standard deviation to represent the normal density. Okay. Yeah, so I think the new things are get to this point. Okay, because now we have observations in groups. And then you first of all need to know how to express the joint density of the observations in one group. And then how to combine them. Well, I guess I should really say the new stuff is up until here. And then whatever after this is what we saw before, but slightly different, of course, but it's the same procedure that we did before. Okay? Yeah, so we're 1 hour in and we only did one. So let's see. And so the other, so this is for 1 mu j, and you have mu, tau, and sigma. Okay? So which one do you want to do? We probably just have time to do one. And then I will leave the rest for you. I can type it up like a derivation and then share with you later. But again, I think going through this will be helpful overall because using JAX is like a black box. You just put in whatever code is there, but you can do it. I mean, it still makes sense. You can still work out all of the details if you were to code up your Gibbs sum for yourself. So pretty much like if you, so maybe let's spend like 1 minute on looking at this full conditional. You need all, so in order to sample this, what do we need? We need all of the data in that group, right? That's the sum of all of the yij. We need the sample, or like, sorry, we need the draw of sigma from previous step, right? We need the draw of mu from previous step, tau from previous step. And then of course you need to know nj, which is the number of observations in that group, which is fixed. Okay, so you know everything. And that goes into your Gibbs step. Okay? All right. So the other one for mu will be another normal. So I think we'll be maybe 2 repeating for what we have done. So let's maybe just pick, which one do you want to do, sigma or tau? So tau is only for the prior related to mu, right? Whereas sigma like appears in the likelihood. So I think sigma is probably, will be a little bit more involved, but probably more interesting to work with. So let's work on sigma really quick, and then we're gonna, yeah, do the lab next week. All right, so what do we have about sigma? Yeah, so sigma, think about it. Remember all of the product, the 2 nested products that we did for the likelihood all have to stay now because sigma is in both. Right? So what do we do? So pi over 1 over sigma squared. So I'm trying to use this again generically for expressing the the full conditional posterior. So what do we have? What do we have from the likelihood? Likelihood was j from 1 to capital J, and then I from 1 to nj, and then we have this density. So again, just to save space and writing time, I'm using yij given mu j and sigma. Okay, so this is the case you see. So and then the f stands for the normal density. So sigma gonna come into play in both terms, one outside of exponential term and also the one inside. Okay, so you have to keep all of them. So maybe it's useful just to write out the density here. So it's what? 1 over 2 pi sigma square, and then negative 2 sigma square yij minus mu j square. Okay? So what I mean is, sigma is here, sigma's here, you have to keep all of the product. So what that means is the contribution from the likelihood, so work it one by one. So first of all, this is what? It's going to be proportional to 1 over sigma square to the power of 1/2, right? Yeah. So what you can do is, so maybe it's easier just to keep the product for now and then later expand it. So you're counting the right number of them. So essentially I have the contribution of this, right? So again, this is a nested product, okay? So you have many of them to do. And the other part is from the exponential term, which this goes into the sum. So yeah, just to like keep consistent, we're doing product. So you can have this intermediate step of making sure that I have all of the terms right. Okay. And then that's from the likelihood. The other part is from the prior, right? The prior is a gamma. So we can throw away those constants, but we should keep 1 over sigma squared raised to the power of alpha sigma minus 1. And then in the exponent term, we have, because it's beta sigma, I think, and then 1 over sigma squared. Okay? Right, so this is all of the terms related to sigma that I have to keep track of. Okay. All right, so how can I do, how can I expand it? Yeah. So first of all, it's 1 over sigma squared to the power of 1/2, and then I product over all of the nj's, and then product over all of the j, capital J's. So essentially what I have is I have 1 over sigma squared, still have, but I'm summing over. So first of all, it's nj. It's fixed, right? I mean, the product, I mean, there's no like subscript about sigma at all. So first of all, I should have nj from each contribution, but because I go from all of the j's as well, so essentially it's going to be j from 1 to capital J. And you might notice this is just going to be n, because that's whatever, how many observations in total that you have. Right? So you can keep it in this way, or just write little n if you define n to be the sample size of the data set. Okay? Make sense? Mm-hmm. And then, oh yeah, maybe let me just like combine the terms now. So you have this, and then you also have the contribution from the prior, right? So it's sigma, alpha sigma minus 1. Okay? Right? And then I can also combine the terms in the exponential term. So what I have is, I can first of all write out my 1 over sigma squared, because that's the common term that I have. And then I have to work it one by one. So for the contribution of the likelihood, I have, okay, I have the sum. So the product is outside, so it goes into the exponential term, it sums, right? So, well, this part, you actually don't have to do too much simplification. It just, all of them become sums. And you're just doing yij minus mu j squared. Oh, I should also have this 1/2 term, right? I think so, right? Because there's a half here, yeah. And then I use that plus the prior contribution, which is the beta sigma. And I think that's what it is, right? And this is a gamma. Okay, so my two gamma parameters. The first one is this. The second one is this. So if I use this as A, this is B, then my full conditional posterior of 1 over sigma squared is gamma A and B. Okay? Yeah, so the one for tau works similarly but less involved because remember tau never goes into the likelihood. Yeah, so you don't have to worry about those joint likelihood there. And the one for mu also, because mu doesn't go into the likelihood either. Okay, so it will be less complicated, but the gist is the same. You go from the process. So before we break, I just want to call your attention to, if you look at what we have in terms of A and B, the two parameters and now we recognize, this is for sigma, right? So the alpha sigma and beta sigma, I mean, they make sense. They are just coming from the prior. But if you look at the other two terms, I mean, the sum of nj over 2 and then whatever is down there, you can see that all of the groups have to come into play when you are determining sigma, right? Like you have all of the capital J groups here, and you're doing two summation down here for the second parameter, right? And this is not surprising because if you remember the model, the data model is Yij is normal, mu j, and sigma, okay? So because sigma is shared, all of the data, Yij, j from 1 to capital J and I from 1 to nj, and all of the mu j, you see that here? They have to all together contribute to the update of your sigma, because that's how the model is set up. Okay, so I don't have it now, but remember earlier when we have the expression for mu j, if you see your notes, when you're looking at mu j, yeah, let me just write it here. I think I have time. So anyway, so this case, you see that because sigma is the single parameter that is being shared across all of the groups. So in the Gibbs update, it makes sense that all of the data as well as all of the group mean, all of them going to contribute to the update of sigma because that's how it is shared. Okay, but previously, so let me write it over here. If you look at the notes that you wrote down earlier about the update from mu j, where do you notice the difference? Or what kind of difference do you notice? When you update the mu j, so let me write it here. So the mu j, I think earlier we have is mu j is normal. Well, it's just sum of Yij divided by sigma squared, sorry, plus mu divided by tau squared over nj over sigma squared plus 1 over tau squared, that's the mean. And the standard deviation is nj over sigma j plus 1 over tau squared, negative 1/2. Okay. So what do you see here? In the model, we have the first stage prior, let's see, what is it, tau, right? And then the data model. Right, this is what we have. So mu j is separate, I mean, well, we do see that they are sharing the same prior, but that's going to be the effect that you're going to have for the mu and tau. So if you were to derive the full conditional posterior for mu and tau, you will see the contribution of those mu j's coming in. But if you only focus on mu j, then only the data in the j's group gonna matter, right? Say, what is it? We have the K-drama example. So in one schedule, like pretty much if I'm looking at schedule 1, and I'm trying to update the mu j, like mu 1 for schedule 1, all of the data points from schedule 2, 3, 4 don't matter. Intuitively makes sense because they don't contribute to the mu j themselves. Okay? But if you also, in this case now, if you have derived the full conditional, you can see that. So here I didn't write it fully, but it's I from 1 to nj, meaning that I'm only looking at observations in j schedule. Right? So here you see that, well, because the model is set up in this way, and then the update like works accordingly. Okay? So I think that's important to notice. I think I have a closing bracket here. That's important thing to keep in mind. And also the thing is, unless we do the derivation, we will never notice this. You were just gonna go with JAX. And so I think it's, yeah, keep this in mind in hierarchical modeling. When you set up the model, it's actually going to affect how the model being estimated later through MCMC techniques. And for this, I still would say simple case because we can derive all of the full conditional posterior distribution. So last time, I think there are some comments. I mean, I show you all about the issues of negative mu and mu j's, and then there was discussion last time about what else you can give for those priors or hyperpriors if I want to make sure that mu j are non-negative and mu is non-negative as well. So that's the lab that I was hoping to do today, but let's not worry about it. Let's do it on Tuesday. So you can start giving other prior distributions for them. And the two examples that we're going to do in the lab, one is a log normal distribution. So if you have a distribution, or if you have a random variable follows a log normal distribution, that means that the exponential of that random variable follows a normal distribution. Okay? And then that can make the original random variable strictly positive. Okay, so that will be an appealing feature for mu and mu j in our case, because we never want negative mean ratings or negative mean ratings of means. Okay, so that's one that we will cover through the lab. I posted already if you want to check it out. We're going to do on Tuesday. Another one that I played with yesterday and I posted as well is instead of like deviate from normal altogether, we can do something called truncated normal. So normal, like it goes from the entire real line, right? The range, yeah. But if I know that my mu in this case represents a mean which should never be negative, I can truncate the normal density and only looking at the non-negative side of it. So essentially, I still have a normal distribution, but I renormalize it by discarding the density that I have below 0, and then keep everything to, I mean, I have to renormalize it a little bit. The shape will still look very similar, but the density, like function, will be slightly different because I have to make sure that I don't have any density below 0. And that is another way that we can make sure that all of the mu j's and mu are non-negative in this particular application. Okay, so that's the plan for the lab, which we're going to come to on Tuesday. And I posted the instructions in Moodle, so if you want to check it out, feel free. And I will also change the due date for that as well. So don't worry about it. So we're going to do that on Tuesday. And yeah, that's all. And this will be uploaded later. And hopefully the derivation exercise is useful and also shed some light on the understanding of the model. Okay.